All right, we're in chapter 6.6, proportions in similar triangles. We're going to work on the triangle proportionality theorem, which states that if a line is parallel to one side of a triangle, intersects the other two sides, then it divides the other two sides proportionally, also known as the side-splitting theorem. So BE, which is parallel to CD, is going to divide the two sides proportionally. Here are the two sides, side AC and side AD. They're the two sides that are being split proportionally, not the bottoms, the two sides. So we can say AB over BC is equal to AE over ED. Top left over bottom left is equal to the top right over the bottom right. So our first problem is going to be this one here. So AB is going to be 12, BC is 4, AE is 15, ED is going to be X. We'll just keep it as ED. So we do our proportions. 12 ED equals 4 times 15, which is 60. Divide both sides by 12. ED is going to be equal to 5. So I come over here and I put a 5 in here. Now remember, for things to be proportional, they have to have the same scale factor. If I take a look at the bottom left-hand number here, 4, top left-hand number is 12. That has a scale factor of 3. Bottom right number is 5. Top right number is 15. Again, same scale factor of 3. Now, if you don't want to use the side-splitting theorem, you can always go back to Old Faithful, which is going to be similar triangles. So triangle ABE is similar to triangle ACD. How do I know that? Because these two angles are equal because they're corresponding angles between parallel lines. These two angles are also equal, again, corresponding angles. So by angle, 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 similarity, that's not looking too good, huh? The two triangles are similar. So we can just go AB over AC, first two letters over the first two letters, next two letters, BE over CD, and first letter, last letter over first letter and last letter. So AB is 12. Be careful here because AC is the whole side, which is going to be 16. We're not using BE and CD, but we are using AE, which is 15. And in this case, AD is going to be the whole side, which is, we'll keep it as AD. So you do your cross multiplication here, and you're going to find out that AD is equal to 20. And if this whole side here is 20, and the top portion is 15, then 15 from 20 is going to be 5. Okay, so we end up at the same place we did by using the side-splitting theorem. So if you're not comfortable with side-splitting theorem, just go back to Old Faithful, which is going to be our similar triangles, and that's always a good way to go. Okay, so let's try another example here. So let's say I have, that's not too good. Try again. Let's say I have big right triangle, and I drop another line in parallel to the other base. Okay, and I'm going to tell you that this is 3, this is 6, this is 4. Let's say I want to use the bottom, find the bottom, and we'll call this okay. Now, if you thought this was side splitting, you would say 3 over 6 which is correct for side splitting, but then you'd put 4 over the x, and you'd be tempted to go 3x is equal to 24, x is equal to 8, and you'd be tempted to say that the bottom is equal to 8. However, this is side splitting, this is not. So if you run into this case, what you should do is go back to Old Faithful, which is similar triangles, triangle FRL, similar to triangle FIE. So then FR goes over FI, RL goes over IE, and FL goes over FE. Plugging the numbers in, FR is 3. FI, be careful, FI is the whole side, which is going to be 9. RL is the number 4, which is given. IE, we don't know, that's what we're looking for. So I have 3 IE equals 9 times 4. 3 IE equals 36. So IE is equal to 12. So you have two answers here. You have IE is 12, and up here you have x is 8, and x was IE. Okay, so which one's correct? Well, the correct one is going to be this one down here, because this was not side splitting. Now let's say I gave you the another number in here, and I told you that FL was equal to 5, and you want to find LE. Well, we can use side splitting for that. We can say 3 over 6, because of the sides being split, is equal to 5 over y, because that's the sides being split. So you're going to have 3y is equal to 30, y is equal to 10. Okay? So that's the correct use of the side splitting theorem. Now, you can work backwards on the side splitting theorem and say, how do you determine if lines are parallel? Well, you determine if lines are parallel if the sides are split proportionally. Okay, so since this works, since 14 over 7 is equal to 16 over 8, they both have the same scale factor of 2, then that means that these lines have got to be parallel to each other. Okay? So the question says, are these two lines parallel to each other? Well, they look like they're parallel. They do not have the markings that are parallel, so they give you some numbers, so we got to figure something out. So we're going to go top left over bottom left equals top right over bottom right. Two options are cross multiply, see if they're the same. In that case, you would do 4 times 15, see if it's equal to 6 times 10. This is going to be 60, that's going to be 60. If they're both equal, then that's good. Another thing is you can reduce each side of the fraction. See if they have the same scale factor, and if they do, that is good too. Okay? So how about if I gave you this example here and I said, are these parallel to each other? And I said, that's 4, that's 2, that's 6, and that's 4 here. And we're asking, are these two lines parallel? Well, by side splitting, you would go 4 over 2 equals 6 over 4. Top left, top right, bottom right. Do some cross multiplication, or you can reduce the fraction, and you should notice that 2 times 6 is 12, 4 times 4 is 16. They are not equal to each other, which means they are not parallel. Okay, so that's how we decide if lines are parallel. Now, We get the same idea if we have more than two parallel lines and you're splitting some transversals, then they're going to divide the transversals proportionally. This is just an extension on the side splitting theorem. So if we take a look at this, you would do 20 over 12 equals x over 10. 12x is equal to 200. Oh, sorry about that. 20 over 12 is equal to x over 10. So 12x is equal to 200. Then divide both sides by 12. So we got 200 divided by 12. And we get 16 2/3. It's okay to have fractions, decimals, it's okay as long as the scale factor is the same. Okay. So how do we find this missing section here? All right, this is really just an extension of the last thing they showed you. Okay, if you draw this longer, then it looks exactly like that previous problem. So we just do 4 over QR is equal to 6 over 10. So we do 6 QRs, 4 times 10, which is 40. Divide both sides by 6. QR equals 40 over 6. We do some fractions here. What do we got there? 20 over 3. So QR is equal to 6 2/3. Go to the next one. Similar fashion. Top left, bottom left, top right, bottom right. So we got 4 BCs equals 6 times 6, which is 36. Divide both sides by 4. BC is equal to 9. Okay. Let's say they gave you multiple lines that are parallel. Definitely not drawn to scale. But we're going to use the side splitting theorem to kind of work through this. So let's say this is 2. We'll go this is 3. This one here is 5. Tell you this is 4. We want to find x and we want to find y. Hopefully you see that the scale factor is a 2-to-1 ratio here. Okay. Top left, middle left equals top right, middle right. X would be equal to 6. Let's say you wanted to find the bottom one here. Top left over bottom left equals top right over bottom right. Y is equal to 10. How about middle left over top left equals middle right over top right. X would equal to 6. How about middle left over bottom left equals middle right, you already found 6, over bottom right. Y is equal to 10. So this is 6, this is 10. You can also tell that this whole side is 10, and this whole side over here is going to be 20. Which is a 2-to-1 ratio. Okay, hope you found this lesson enjoyable, and I look forward to some practice problems. Have a great day.